160 f x equals qxpx, where degree of p x is less than degree of q x. If not, we can apply long division to write f x as a sum of a polynomial and a rational function with the desired property. The first step in this method is to factorize the denominator q x into linear factors, if possible. The case where we have irreducible quadratic factors of q x will not be treated here. Now, with each linear factor x plus b m of multiplicity m, we associate constants a1, a2, am and write 2, 1, 2, xb, axba, plus, with the ais to be determined. Then, the rational function f x is then expressed as a sum of simple rational functions and can be easily integrated. Example 4.90. Find dxx412 solution by factorizing x2, 4 as x, 2, x plus 2. We have 412x equals 2, 2, 1. X equals x2a plus x2b equals 2, 2, 2, 2. XX AXBX. Since the denominators are equal, we equate the numerators as a, x plus 2, plus b, x, 2, equals 1. From equality of polynomials, we get 2210 a equals 1 4 and b equals 4 1. Hence, dxx412 equals dxxx214214 equals 41x2 dx. 41x2 dx equals 41nx 2. 41nx plus 2 plus c. Example 4.91. Find dxxxxxx. 231322. Solution: the denominator x3, x2, 2x equals xx2, x, 2, equals xx plus 1, x, 2, has 3 roots 0, -1, and 2. xxxxx231322 equals 1, 2, 3, 1, 2. xxxxx equals xa plus x1b plus x2c equals 1, 2, 1, 2, 2, 1. xxx axxbxxcxx a x plus 1, x, 2, plus bxx, 2, plus cx, x plus 1, equals 3x2 plus x, 1. This equation is true for all xr. In particular, when x equals 0, a 1 minus 2 equals minus 1, a equals 1 2. When x equals minus 1, b minus 1 minus 3 equals 1, b equals 1 3. When x equals 2, c 2 3 equals 13, c equals 13 6. 161. Hence, dxxxxxx 231322 equals 21x dx plus 31x1 dx plus 613x2 dx equals 21nx plus 31nx plus 1 plus 613nx. 2 plus c. The definite integral. For a very long time, mathematicians have struggled with the problem of finding areas of plane regions. Until the invention of the integral calculus, however, the regions considered were mostly those regions bounded by straight lines, called polygons, with a few exceptions such as the circle and the ellipse. The Greek mathematicians found the area of a polygon by first finding the area of a rectangle, then finding the area of a parallelogram, and then finding the area of a triangle. The area of a polygon can be used to approximate the area of a region bounded by curved boundaries. For instance, the area of a circle can be found by drawing a sequence of inscribed polygons P4, P8, P16, Pn, and then taking limit as n. To develop the idea for more general regions, consider the region bounded by the graphs of y equals 2x2 plus 1, x equals 0, x equals 6 and x-axis. To find the area of the region, let us identify the region S by drawing its boundaries, namely the graphs of y equals f, x equals 2x2 plus 1, x equals 0, x equals 6 and the x-axis as shown in figure 4.21. Figure 4.21. Unfortunately, since f, x equals 2x2 plus 1 is a curve that is not a line segment, we cannot find the area of the region by the elementary methods. So, it is necessary to develop a stronger technique that also generalizes the elementary method and enables us to find the area of such regions. Let A, S, denote the area of the region S. It is not difficult to give lower and upper bounds of A, S. For instance, we consider the rectangle R that is enclosed by the boundaries of S and the rectangle R that encloses S, as shown in figure 4.22. 162. Figure 4.22. Then A, R, equals 6 and A, R, equals 673 equals 438. Hence 6a, s, 438, which gives a wide range of bounds of a, s. Better bounds of a, s, can be obtained if we consider the finer rectangles R1, R2, R3, R4, R5, and R6 that are enclosed by the boundaries of S and R1, R2, R3, R4, R5 and R6 that enclose S as shown in Figure 4.23. Figure 4.23. Figure 4.23 evidently, each of the rectangles has base 1 unit but varying heights. It follows that a, R1, plus a, R2, plus a, R6, a, s, a, R1, plus a, R2, plus a, R6, i.e. 61a, R, IIA, S. 6. 1a, IRI which gives 116a, S. 188. To give a formal definition of the subdivisions, for any positive integer n, divide a, b into subintervals by introducing points of subdivision x0, x1, xn. Definition 4.14, a partition of a, B is a finite set P of points x0, x1, xn such that A equals x0. 163. The length of any subinterval 11-1, 11 of a partition P is defined and given by 11 equals 11. 11-1 in particular, when the lengths of each subintervals are equal, it is called a regular partition. In this section we shall consider only regular partitions, so that the length of each subinterval is 11 equals 11, 11-1 equals NBA. Having chosen a partition P of A, B, we inscribe and circumscribe rectangles on the region R using the division points of P as seen in Figure 7.3, A, and B. Since F is continuous on A, B, by the maximum-minimum theorem, for each I between 1 and n, there is a minimum value μ and a maximum value μ of f on the subinterval 11-1, 11. If Ri and Ri denote the inscribed and circumscribed rectangles on 11-1, 11, respectively, then the area of Ri is A. Ri equals μ11 and the area of Ri is A. Ri equals μ11, since the base of both Ri and Ri is 11 equals 11, 11-1. From our observation in Figure 7.3, A, and B, we see that the area of the region R is between the sum of the inscribed rectangles and the sum of the circumscribed rectangles. Definition 4.15. let F be continuous on A, B and P be any partition of A, B. The sum LF, P, equals M1x1 plus M2x2 plus Mnxn is called the lower sum of F associated with P, and the sum UF, P, equals M1x1 plus M2x2 plus Mnxn is called the upper sum of F associated with P. From our construction we see that if P is any partition of A, B, then the area of R should be between LF, P, and UF, P, i.e. Example 4.92, let f, x, equals x2 for OX2 and let P equals 2231, 210, be a partition of 0, 2. Then the subdivision of 0, 2 associated with P are 210, 121, 231, 223. Since x2 is an increasing function on 0, 2, the minimum value of f on each subinterval is at the left endpoint and the maximum value of f at the right endpoint. Thus, m1 equals f, 0, equals 0, m2 equals f4 121, m3 equals f, 1, equals 1, m4 equals f4 923, and m1 equals f4 121, m2 equals f, 1, equals 1, m3 equals f4 923, m4 equals f, 2, equals 4. The base of each subinterval is 11 equals 420 equals 21. Thus the lower sum of f associated with P is LF, P, equals 0. 21 plus 4 1. 21 plus 1. 21 plus 4 9. 21 equals 4 7. And the upper sum of f associated with P is LF, P, area, R, UF, P. 164. UF, P, equals 4 1. 21 plus 1. 21 plus 4 9. 21 plus 4. 21 equals 415. Therefore the area of the region R below the graph of f, x, equals x2 above the x-axis on 0, 2 is between 4 7 and 4 15, i.e. 4 7 area, R, 4 15. Definition 4.16, let f be continuous on A, B. The definite integral of f from A to B is the unique number I satisfying LF, P, IUF, P, for every partition P of A, B. This integral is denoted by I equals BAF, x, dx. The numbers a and b are called the lower and upper limits of integration, respectively. Note that as the number of subdivisions of an interval a, b increases, the minimum and the maximum values of f on 11-1, 11 are close to each other. For each I from 1 to n, if we take an arbitrary number ti in 11-1, 11, then we get the sum niiif tx1 equals f t1 x1 plus f t2 x2 plus f tn xn. This sum is called a Riemann sum or an integral sum. Even though it is sometimes possible to calculate b af x dx by finding formulas for lower and upper sum, we are to evaluate it here by the use of the fundamental theorem of calculus. For the moment we can conclude that if f is continuous and non-negative on a, b, then the area of the region R between the graph of f and the x-axis on a, b is given by area R equals b af x dx. Remark: the definite integral has the following properties. If f and g are integrable over a, b and k is a constant, then a, b, a kf x dx equals kb af x dx. b ba f x g x dx equals baf x dx bag x dx. c. If f x 0 for axb, then b af x dx 0 and if f x 0 for axb, then baf x dx 0. d. If mf x m for all x a, b, then 165 m b a baf x dx m b a e. If c is any number in a, b, then baf x dx equals caf x dx plus bcf x dx. Additive property. f aaf x dx equals 0 for any number a. g abf x dx equals baf x dx. To develop a general method for evaluating baf x dx without computing lower and upper sums, we shall state the most important theorem in calculus, the fundamental theorem of calculus. To this end, let f t be continuous on a, b. Then f is integrable on a, b, and for any x a, b the definite integral xaf x dt exists. Define a function f on a, b as f x equals xaf t dt. In effect, the fundamental theorem of calculus states that the function f x is differentiable with derivative f x, thereby eliminating the integral by the derivative. It also shows us how to evaluate the definite integral. Remarks. A. From 2. To evaluate BAF x dx, all we have to do is to find an antiderivative of f and find the difference of its values at a and at b. This is usually denoted by BAF x or ABF x to mean f b f a b. If f is an antiderivative of f, then f x plus c for any constant c is also an antiderivative of f. But since BAF x c equals f b plus c, f a plus c equals f b f a equals BAF x, the constant c does not play any role in evaluating the definite integral. Thus we can always take c equals 0. Theorem 4.22. Fundamental theorem of calculus. Let f t be continuous on a, b, and for each x a, b let f x equals then I f x is a differentiable function with f x equals f x. 2. If f is any antiderivative of f on a, b, then equals f b f a. 166. Example 4.93. Let f x equals x2 for 0 x2. Then f x equals 331 x is an antiderivative of f, so that by the fundamental theorem of calculus, 202x dx equals 331x02 equals f 2 f 0 equals 3231. 3.031 equals 038 equals 38. From our previous discussion, the area of the region R under the graph of f x equals x2 on 0, 2 above the x-axis is thus 202x dx equals 83 square units. Example 4.94. Evaluate each of the following definite integrals a, x dx 413b, x dx 0 sin c 2 0 x cos dxd 103 5x2 xe dxx. Solution. A. Since f x equals 3 2 x equals 2x, x is an antiderivative of f x equals 3x, we have 403x dx equals f 4 f 1 equals 2 4 2 1 1 equals 16 to 2 equals 14. B. An antiderivative of sinx is cos Thus 0 sin x dx equals cos 0 equals cos 0 equals dash minus 1 plus 1 equals 2. C 0 cos x dx equals 2. 2 sin 2x equals 182. 0 plus 0 equals 182. D x e dx x 5 2 103 equals 104.245 x e equals 1e45. 0 plus 0 to 1 equals e413. Remark: for functions that are given by more than one formula, we evaluate the definite integral using the additive property. Example 4.95. Evaluate x dx 1 to 1. Solution: by definition x plus 1 equals 1, 1, 1. 1x for x for x. Y then by additive property, we have 167 x dx 1 2 1 equals x dx 1 2 1 plus x dx 1 1 1 equals 1 2 2 2 x plus 1 1 2 2 x Figure 4.23 equals 1 2 2 2 1 plus 1 2 1 1 2 1 equals 2 2 1 equals 5 2. From the method of integration by substitution, we have f g x dx equals f u do where u equals g x. If we are to evaluate this integral between a and b, we have, when x equals a, u equals g a, and when x equals b, u equals g b. Thus it follows. Change of variable. Example 4.96. Evaluate x dx 3. 224. Solution: we have two possibilities to evaluate such a definite integral. One way is to find an antiderivative of 4 2x and evaluate it between 2 and 3 by the fundamental theorem of calculus. The other is to use the change of variable formula and change the limits of integration before integrating. To this end, let u equals g x equals x2, 4. Then do equals 2x dx. When x equals 2, u equals g, 2, equals 0, and when x equals 3, u equals g, 3, equals 5. Thus x dx 3. 224 equals 23. 0. Do u equals 5. 0 1 2 2 1 u do equals 5302. 21 UU equals 0.5. 531, 0 equals 355. Application of the definite integral. Area. The definite integral has several applications such as finding areas of regions, arc length of curves, surface areas, and volumes of solids of revolution. In this section we shall see how to find areas of plane regions with curved boundaries using the definite integrals. In the previous section we have seen that if f, x, 0 for all x a, b, and if f is continuous on a, b, then b, a f, x, dx gives the area of the region R below the graph of f, above the x-axis, between 168. The lines x equals a and x equals b. For instance, if f, x, equals x2 for 0 x2, then the area of R as given in is given by a, R, equals 830232032x dx square units. If f, x, 0 on a, b, then taking g, x, equals f, x, 0 for a x b, the area of the region R below the x-axis, above the graph of f on a, b is given by a, R, equals bag, x, dx equals baf, x, dx equals baf, x, dx. For instance, if f, x, equals 2x for minus 2x0, then the area of the region R below the x-axis, above the graph of f on minus 2, 0 is given by a, R, equals 0 to f, x, dx equals 0 to 2x dx equals x2 to 0 equals dash 0 to 4 equals 4 square units. Now let f and g be continuous on a, b, and assume that f, x, g, x, for a x b. Then the area of the region R below the graph of f, above the graph of g, and between the lines x equals a and x equals b is given by a, R, equals fx gx dx ba. Example 4.97. Find the area of the region bounded by f, x, equals 2x, g, x, equals x and line x equals 9. Solution. Sketching the graphs of y equals f, x, y equals g, x, and x equals 9. The region R can be identified as shown in Figure 4.24. Figure 4.24. It follows that a, R, equals 9090 f, x, g, x, dx 2x x dx 2334x plus 76.59202x. Y 9x. Y equals 2. R. Y equals X. 169. Exercise 4.4. 1. Evaluate the following indefinite integrals: a. x3 plus 5 dxd, 4. x plus 3x2, 2x5 dx. b. 2x8 dxe, cos 4x dx. c. 3 sinx f dxxxx 2 3 4. 2. Find the following integrals by substitution: a. x3 dxc, xx dx sin cos 2. b. e dx x3d, dxx n x4. 3. Find the following integrals by the method of integration by parts: a. xx dx cos c, dxx n x2. b. x dx x, 1, 3d, xx dx sin 2. 4. Integrate the following by the method of partial fractions: a. x2, 3x4, dxc, x1, x2, x3, dx. b. 6 2xxxd, dxxx 2 2. 5. Find the area of the region R between the graph of f and the x-axis on the given interval a, f, x, equals x2 plus 1, on 1, 3b, f, x, equals 2 plus cos, on 0 3 2. c, f, x, equals x1, on 1, 4. d, f, x, equals x, 1, on dash 1, 2 6. Find the area of the region between the graphs of the following functions: a, f, x, equals x2 and g, x, equals 2, x. b, f, x, equals x, x equals minus 1, x equals 3 and the x-axis. c, f, x, equals x2, 4 and g, x, equals 4, x2. 170. References: 1. Alamayahu Haile and Yismael Mu, Mathematics an Introductory Course, Department of Mathematics, Addis Ababa University 2. Demisu Jemida and Said Mohammed, Fundamental Concepts of Algebra, AAU 3. Edwin J. Purcell, Dale Varberg, Calculus with Analytic Geometry 4. G. Chartrand, A. D. Polamini and P. Zhang, Mathematical Proofs, A Transition to Advanced Mathematics 3rd edition, Pearson Education, Inc. 5. Goodman Hirsch, Precalculus Understanding Functions, 2000. Chapter 3. Matrices, Determinant, and Systems of Linear Equation. Matrices, which are also known as rectangular arrays of numbers or functions, are the main tools of linear algebra. Matrices are very important to express large amounts of data in an organized and concise form. Furthermore, since matrices are single objects, we denote them by single letters and calculate with them directly. All these features have made matrices very popular for expressing scientific and mathematical ideas. Moreover, application of matrices are found in most scientific fields, such as economics, finance, probability theory, and statistics, computer science, engineering, physics, geometry, and other areas. Main objectives of this chapter. At the end of this chapter, students will be able to understand the notion of matrices and determinants. Use matrices and determinants to solve system of linear equations. Apply matrices and determinants to solve real-life problems. 3.1 Definition of matrix. Consider an automobile company that manufactures two types of vehicles, trucks, and passenger cars in two different colors, red and blue. The company's sales for the month of January are 15 trucks and 20 passenger cars in red color, and 10 trucks and 16 passenger cars in blue color. This data is presented in Table 1. Table 1. Trucks, passenger cars. Red 1520. Blue 1016. The information in the table can be given in the form of rectangular arrays of numbers as C1 C2 R1 15 20 R2 10 16. In this arrangement, the horizontal and vertical lines of numbers are called rows, R1, R2, and columns, C1, C2, respectively. The columns C1 and C2 represent the trucks and passenger cars, respectively, which are sold in January. And the rows R1 and R2 represent 105. The red and blue colored vehicles, respectively. An arrangement of this type is called a matrix. Note that the above matrix has 2 rows and 2 columns. This shows us the usefulness of matrix to organize information. Definition 3.1. Definition of matrix. If m and n are positive integers, then by a matrix of size m by n, or an m times n matrix, we shall mean a rectangular array consisting of mn numbers, or symbols, or expressions in a boxed display consisting of m rows and n columns. This can be denoted by C1 C2 C3 CN R1 A11 A12 A13 A1 N R2 A21 A22 A23 A2 N R3 A31 A32 A33 A3 N. Rm M1 M2 M3 AMN, where R1, R2, R3, Rm, and C1, C2, C3, Cn represent the M rows and N columns, respectively. Remark. One note that the first suffix denotes the number of a row, or position, and the second suffix that of a column, so that ij appears at the intersection of the ith row and the jth column. 2 matrix A of size M times N may also be expressed by A equals ij M times N, where ij represents the I, J, th entry of the matrix ij. Example 3.1. The following are matrices of different size. A equals A B C D is a 2 times 2 matrix. B equals A B C B C D C D E is 3 times 3 matrix. C equals 1 2 2 3 3 4 4 5 is 4 times 2 matrix. D equals 1 2 3 4 is 4 times 1 matrix. E equals A B C D B C D E is 2 times 4 matrix. F equals B C D E is 1 times 4 matrix. 106. Definition 3.2. Matrices which are n times 1 or 1 times n are called vectors. Thus, the n times 1 matrix A equals A11 A21 A2n is called a column vector, and the 1 times n matrix B equals B11 B12 B1n is called a row vector. Definition 3.3. Submatrix. Let A be an M times n matrix. A submatrix of matrix A is any matrix of size R times S with R less than or equal to M and S less than or equal to N, which is obtained by deleting any collection of rows and / or columns of matrix A. Example 3.2. For the given matrix A equals 1 2 3 2 3 4 3 4 5 I 1 2 3 2 3 4 is a submatrix of A, which is obtained by deleting the third row of A. 2 1 3 2 4 3 5 is a submatrix of A, which is obtained by deleting the second column of A. 3 3 4 4 5 is a submatrix of A, which is obtained by deleting the first column and first row of A. Definition 3.4. Equality of matrices. 2 matrices of the same size, A equals ij M times N and B equals bij M times N, are said to be equal, and write A equals B, if and only if ij equals bij, for all ij. Example 3.3. A. Determine the values of A, B, C and D for which the matrices A and B are equal. A equals 5, 4, 0, 2, B equals A, B, C, D. Solution. By definition 3.4, we have A11 equals B11 implies A equals 5. A12 equals B12 implies B equals 4. A21 equals B21 implies C equals 0 and A22 equals B22 implies D equals 2. 107. B. Find the values of alpha and beta for which the given matrices A and B are equal. A equals 1, 2, 3, 1, B equals alpha beta 2 alpha 1. Solution. Similarly, we have A11 equals B11 implies alpha beta equals 1. A21 equals B21 implies alpha equals 3, and hence beta equals 2. Definition 3.5. Zero matrix. An M times N matrix A equals Ij is said to be the zero matrix if Ij equals 0 for all Ij. Example 3.4. The following are zero matrices. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Exercise 3.1. 1. Write out the matrix of size 3 times 3 whose entries are given by Zij equals I plus J. 2. Write out the matrix of size 4 times 4 whose entries are given by Zij equals 1 if Ij 0 if I equals J. 1 if I. 3 for the matrix A equals 1, 2, 3, 2, 3, 4, 3, 4, 5. Give all the submatrices of size 2 times 2. 3.2 Matrix algebra. In this section, we discuss addition of matrices, scalar multiplication, and matrix multiplication. 3.2.1 Addition and scalar multiplication. Addition and scalar multiplication are the basic matrix operations. To see the usefulness of these operations, let us observe the following simple application. 108. Consider again an automobile company that manufactures two types of vehicles, trucks, and passenger cars in two different colors, red and blue. If the sales for the months of January and February, respectively, are given by J equals 15, 20, 10, 16 and F equals 12, 28, 20, 14. Then the total sales for 2 months can be given as follows. The total number of red trucks sold in 2 months is 15 plus 12 equals 27. Similarly, the total number of blue trucks, red passenger cars and blue passenger cars sold in the 2 months are given by 10 plus 20 equals 30. 20 plus 28 equals 48 and 16 plus 14 equals 30, respectively. The preceding computations are examples of matrix addition. We can write the sum of 2 times 2 matrices indicating the sales of January and February as J plus F equals 15 20 10 16 plus 12 28 20 14 equals 15 plus 12 20 plus 28 10 plus 20 14 plus 16 equals 27 48 30 30. Definition 3.6. Let A equals ij m times n and B equals bij m times n be two matrices of the same size. Then the sum of A and B, denoted by A plus B, is the m times n matrix defined by the formula A plus B equals ij plus bij. The sum of two matrices of different sizes is undefined. Example 3.5. For the given matrices A, B, C, D, compute A plus B and C plus D. A equals A B C D, B equals W X Y Z. C equals 104. 111, D equals 110023. Solution. Using definition 3.6, we have A plus B equals A B C D plus W X Y Z equals A plus W B plus X C plus Y D plus Z. And C plus D equals 204. 111 plus 110023 equals 314. 114. 109. Theorem 3.1. Laws of matrix addition. Let A, B, C be matrices of the same size m times n. 0 the m times n 0 matrix. Then 1 closure law of addition, A plus B is an m times n matrix. 2 associative law, A plus B plus C equals A plus B plus C. 3 commutative law, A plus B equals B plus A. 4 identity law, A plus 0 equals A. 5 inverse law, A plus A equals 0. Definition 3.7. Scalar multiplication. Let A equals ij be an m times n matrix, and alpha a scalar. Then the product of the scalar alpha with matrix A, denoted by alpha A, is defined by alpha A equals ij m times n. Example 3.6. Consider the automobile manufacturing company once again. Suppose the company's sales for the months of January and March, respectively, are given by J equals 15, 20, 10, 16, and M equals 18, 22, 14, 20. A. If the sales of January is to be doubled in February, then the sales of February should be 2J equals 2, 15, 2, 20, 2, 10, 2, 16, equals 30, 40, 20, 32. B. If the sales of March is to be declined by 50% in April, then the sales of April should be 1, 2, J equals 1, 2, 18, 1, 2, 22, 1, 2, 14, 1, 2, 20, equals 9, 11, 7, 10. Example 3.7. Given the matrices A and B, compute for A and A plus 1, B. A equals 1, 2, 3, 4, B equals 2, 4, 1, 3. Solution. Using definition 3.7, we have 4A equals 4, 1, 2, 3, 4 equals 4, 1, 4, 2, 4, 3, 4, 4, equals 4, 8, 12, 16. And, from the definitions 3.6 and 3.7, we have A plus 1, B equals 1, 2, 3, 4 plus 1, 2, 4, 1, 3 equals 1, 2, 3, 4 plus 2, 4. 1, 3 equals 1, 2, 2, 1. 110. From this example, we observe that the difference of two matrices A and B, which is denoted by AB, can be defined by the formula AB equals A plus 1, B equals IJ bij M times N. Theorem 3.2, Laws of Scalar Multiplication. Let A, B be matrices of the same size M times N, and alpha and beta scalars. Then 1. Closure law of scalar multiplication. Alpha A is an M times N matrix. 2. Associative law. Alpha, beta A, equals alpha beta A. 3. Distributive law. Alpha A plus B equals alpha A plus alpha B. 4. Distributive law. Alpha plus beta A equals alpha A plus beta A. 5. Monoidal law. 1A equals A. Example 3.8. Let A equals 1, 2, 0, 1, B equals 2, 0, 1, 1, C equals A, B, C, D. Be the given matrices. Then 2. A plus B equals 2, 1 plus 2, 2 plus 0, 0 plus 1, 1 plus 1 equals 2, 3, 2, 1, 2 equals 2, 3, 2, 2, 2, 1, 2, 2 equals 6424. And 2a plus 2b equals 2, 1, 2, 2, 2, 0, 2, 1 plus 2, 2, 2, 0, 2, 1, 2, 1 equals 2402 plus 4022 equals 6424. Thus, we have 2a plus b equals 2a plus 2b. Example 3.9. Solve for x in the matrix equation 2x plus a equals b, where a equals 4, 0, 2, 2, and b equals 6, 4, 8, 0. Solution: we begin by solving the equation for x to obtain 2x equals b. A implies x equals 1, 2, ba. Thus, we have the solution. X equals 1, 2, 6, 4, 4, 0, 8, 2, 0, 2 equals 1, 2, 2, 4, 10, 2 equals 1, 2, 5, 1. 111. 3.2.2 Matrix multiplication. Another important matrix operation is matrix multiplication. To see the usefulness of this operation, consider the application below, in which matrices are helpful for organizing information. A football stadium has 3 concession areas, located in south, north, and west stands. The top-selling items are peanuts, hot dogs and soda. Sales for one day are given in the first matrix below, and the prices, in dollar, of the 3 items are given in the second matrix. Note that the price per peanuts, hot dogs, and soda are given by $2, $3 and $2.75, respectively. Peanuts, hot dogs, sodas south stand 120, 250, 305 north stand 207, 140, 419 west stand 29, 120, 190. 2.003.002.75. To calculate the total sales of the 3 top-selling items at the south stand, multiply each entry in the first row of the matrix on the left by the corresponding entry in the price column matrix on the right and add the results. Thus, we have 120, 2.00, plus 250, 3.00, plus 305, 2.75, equals $1,828.75, south stand sales. Similarly, the sales for the other 2 stands are given below. 207, 2.00, plus 140, 3.00, plus 419, 2.75, equals $1,986.25, North Stand sales. 29, 2.00, plus 120, 3.00, plus 190, 2.75, equals $940.50, West Stand sales. The preceding computations are examples of matrix multiplication. We can write the product of the 3 times 3 matrix indicating the number of items sold and the 3 times 1 matrix indicating the selling prices as shown below. 120, 250, 305, 207, 140, 419, 29, 120, 190. 2.00, 3.00, 2.75 equals 1,828.75, 1986.25, 940.5. The product of these matrices is the 3 times 1 matrix giving the total sales for each of the 3 stands. 112. Definition 3.8, Matrix multiplication. Let A equals ij m times n and B equals bij n times pb2. Matrices. Then the product of A and B, denoted by AB, is an M times P matrix whose I, J, Th entry is defined by the formula Abij equals xn, k equals 1, I kj equals ai1b1j plus ai2b2j plus ai3b3j plus in j. In the other words, the I, J, Th entry of the product of is obtained by summing the products of the elements in the ith row of A with corresponding elements in the jth column of B. The above definition can be understood as follows. If A equals A11 A12 A1n has only one row, R1, and B equals B11 B21 Bn1 has only one column, C1, then product of is given by AB equals R1 C1 equals A11 A12 A1n B11 B21 Bn1 equals A11 B11 plus A12 B21 plus A1n Bn1. If A has m rows R1, R2, Rm, and B has n columns C1, C2, Cp, then the product of can be given by the formula AB equals R1 C1 R1 C2 R1 Cp R2 C1 R2 C2 R2CP, RMC1, RMC2, RMCP. That is, the I, J, th entry of AB is RICJ. Remark. The product above two matrices A and B is defined only if the number of columns in A and the number of rows in B are equal. 113. Example 3.10. Let A equals A11, A12, A13, A21, A22, A23, and B equals B11, B12, B21, B22, B31, B32. B2 matrices. Clearly, the product of is defined in this case, since the number of column of A and the number of rows of B are equal. Thus, we have AB equals R1C1, R1C2, R2C1, R2C2 equals A11, B11 plus A12, B21 plus A13, B31, A11, B12 plus A12, B22 plus A13, B32, A21, B11 plus A22, B21 plus A23, B31, A21, B12 plus A22, B22 plus A23, B32. In this example, the matrices A and B, respectively, are 2 times 3 and 3 times 2 matrices, whereas the product of is a 2 times 2 matrix. Example 3.11. Compute the product of the given matrices. A equals 1, 2, 3 and B equals 1, 1, 1, 1, 1, 2. Solution. The product of is defined since the number of columns in matrix A and the number of rows in matrix B are equal. Thus, we have AB is given by 1, 2, 3, 1, 1, 1, 1, 1, 2 equals 1, 1 plus 2, 1 plus 3, 1, 1, 1 plus 2, 1 plus 3, 2 equals 6, 5. Note that the product BA is not defined in this case. Example 3.12. Let A equals 0, 1, 0, 0 and B equals 1, 0, 0, 0 be the given matrices. Then, we have AB equals 0, 1, 0, 0, 1, 0, 0, 0 equals 0, 0, 0, 0. And BA equals 1, 0, 0, 0, 0, 1, 0, 0 equals 0, 1, 0, 0. In this example, we observe that both the products AB and BA are defined. This is true in general, i.e., the products AB and BA are defined for any 2 square matrices A and B of the same size. For the matrices A and B given above, we have AB 6 equals BA. Hence, matrix multiplication is not commutative. Example 3.13. Consider the following diagonal matrices. A equals A 11 0 0 0 A 22 0 0 0 A 33, and B equals B 11 0 0 0 B 22 0 0 0 B 33. The product of is given by of equals A 11 0 0 0 A 22 0 0 0 A 33. B 11 0 0 0 B 22 0 0 0 B 33 equals A 11 B 11 0 0 0 A 22 B 22 0 0 0 A 33 B 33. 114. Similarly, we have BA equals B 11 A 11 0 0 0 B 22 A 22 0 0 0 B 33 A 33. In this case, we have A equals BA, and hence the given matrices A and B commute. More generally, if A and B are any two diagonal matrices of the same size, then A equals BA. Theorem 3.3. Matrix multiplication is associative, i.e., whenever the products are defined, we have A, B, C equals AB, C. From Theorem 3.3, we shall write ABC for either A, B, C, or AB, C. Also, for every positive integer n, we shall write n for the product AAA, n terms. Theorem 3.4. If all multiplications and additions make sense, the following hold for matrices A, B, C and alpha, beta scalars. 1a, alpha b plus beta c, equals alpha, ab, plus beta, ac. 2, alpha b plus beta c, a equals alpha, ba, plus beta, ca. Exercise 3.2. 1. Find your own examples. I. 2 times 2 matrices A and B such that A6 equals 0, B6 equals 0 with AB6 equals BA. 2. 2 times 2 matrices A and B such that A6 equals 0, B6 equals 0 but AB equals 0. 3. 2 times 2 matrices such that A2 equals I2 and yet A6 equals I2 and A6 equals I2. 2. Let A equals 1 1 3 3. Find all 2 times 2 matrices, B such that AB equals 0. 3. Let A equals 1 2 3 4 and B equals 1 2 1 C. Is it possible to choose C so that AB equals BA? If so, what should be the value of C? For given the matrices A equals 1 3 2 4, B equals 1201, and C equals 2140 and alpha a scalar. I compute the products A, B, C, of C, and verify that A, B, C, equals of C. To compute the products alpha, of alpha A, B, A, alpha B, and verify that alpha, of equals alpha A, B equals A, alpha B. 115. 5. Consider the automobile producer whose agency's sales for the month of January were given by J equals 15, 20, 10, 16. Suppose that the price of a truck is $200 and that of a passenger car is $100. Use matrix multiplication to find the total values of the red and blue vehicles for the month of January. 3.3 Types of matrices. There are certain types of matrices that are so important that they have acquired names of their own. In this section we are going to discuss some of these matrices and their properties. Definition 3.9 Square matrix. A matrix A is said to be square if it has the same number of rows and columns. If A has n rows and n columns, we call it a square matrix of size n. Example 3.14. The following are square matrices. A equals A, B, C, D. Square matrix of size 2. B equals 1 2 1 0 1 3 4 2 2. Square matrix of size 3. C equals C11 C12 C1N C21 C22 C2N CN1 CN2 CNN. Square matrix of size n. Definition 3.10 Identity matrix. A square matrix A equals ij n times n is called an identity matrix if ij equals 1. If I equals J0, otherwise, and it is denoted by n. Example 3.15. The following are identity matrices. I2 equals 1001, identity matrix of size 2. 116. I3 equals 1000100001. Identity matrix of size 3. N equals 10 001 0 0 1. Identity matrix of size n. Definition 3.11 Diagonal matrix. A square matrix D equals Dij n times n is said to be diagonal if Dij equals 0 whenever I6 equals j. Less formally, D is said to be diagonal when all the entries off the main diagonal are 0. Example 3.16. The following are diagonal matrices. D equals 1 0 0 1, diagonal matrix of size 2. D equals 2 0 0 0 4 0 0 0 5. Diagonal matrix of size 3. D equals 0 0 0 0 3 0 0 0 2. Diagonal matrix of size 3. D equals 0 0 0 0 0 0 0 0 0. Diagonal matrix of size 3. Note that the identity matrix is the special case of diagonal matrix where all the entries in the main diagonal are 1. Definition 3.12. Scalar matrix. A diagonal matrix in which all diagonal entries are equal is called a scalar matrix. Example 3.17. The following are scalar matrices. A. 3 0 0 3, B. 2 0 0 0 2 0 0 0 2. C. 1 0 0 0 1 0 0 0 1. Definition 3.13. Triangular matrix. A square matrix A equals ij n times n is said to be lower triangular if and only if ij equals 0 whenever ij. 117. Example 3.18. I. 3210270003 011000000 000040000. Upper triangular matrices. 2. 3 0 0 1 2 0 2 4 3 0 0 0 1 0 0 0 2 0 1 0 0 0 2 0 0 0 3. Lower triangular matrices. Remark. A. In the lower triangular matrix all the entries above the main diagonal are 0, whereas in the upper triangular matrix all the entries below the main diagonal are 0. B. Any diagonal matrix is both upper and lower triangular. Definition 3.14. Transpose of matrix. Let A equals ij be an M times N matrix. Then by the transpose of A we mean the N times M matrix, denoted by et, whose I, J, Th entry is the J, I, Th entry of A. More precisely, if A equals ij M times N, then et equals ij N times M. That is, A equals A11 A12 A1 N A21 A22 A2 N. M1 M2 AMN. Then AT equals A11 A21 M1 A12 A22 M2 A1 N A2 N ANM. Note that the kth row of matrix A becomes kth column of et, and the kth column of A becomes kth row of et. Example 3.19. Compute the transposes of the following matrices. A equals 1 1 1 1 2 3, B equals 2 1 3 1 5 3 3 3 7. Solution. First let us consider matrix A. Now, row 1 of matrix A becomes column 1 of it, and row 2 of A becomes column 2 of it. Thus, we have AT equals 1 1 1 2 1 3. Similarly, BT equals 2 1 3 1 5 3 3 3 7. 118. Definition 3.15. Symmetric matrix. A square matrix A is said to be symmetric if A equals it. Example 3.20. Distinguish whether the given matrix is symmetric or not. A equals 2 1 3 1 5 3 3 3 7. B equals 1 1 3 1 2 2 3 2 3. Solution. A. For the matrix A equals 0 1 3 1 0 2 3 2 0. Et equals 0 1 3 1 0 2 3 2 0. Thus, we have A6 equals it. And hence A is not symmetric. B. For the matrix B equals 1 1 3 1 2 2 3 2 3. BT equals 1 1 3 1 2 2 3 2 3. Thus, we have B equals BT, and hence B is symmetric. Theorem 3.5. Properties of matrix transpose. When the relevant sums and products are defined, and alpha is a scalar, then 1. Et T equals A. 2. A plus B, T equals it plus BT. 3. Alpha A, T equals alpha, et 3. T equals BT at. Exercise 3.3. For the given matrices A equals 1 1 3 2, and B equals 3 2 0 1. A. Show that, et T equals A. B. Show that, A plus B, T equals it plus BT. C. Show that, for A, T equals 4, et D. Show that, T equals BT at 119. 3.4 Elementary row operations. Elementary row operations are useful to find the rank of a matrix. See section 3.6. To compute the determinants of matrices. See section 3.7. And to find the inverse of a matrix. See section 3.8. Furthermore, elementary row operations are widely used in solving systems of linear equations. See section 3.9. In this section, we introduce the elementary row operations and apply these operations to transform the given matrix into different form. Definition 3.16 Elementary row operations. Let A be an M times N matrix. The following are known as elementary row operations. 1. Interchanging two rows. Ri left right arrow Rj. Rule of interchanging. 2. Multiplying a row by a non-zero scalar. Ri rightward arrow Re. Alpha is a non-zero scalar. Rule of scaling. 3. Adding a multiple of one row to another. Ri rightward arrow Ri plus alpha Rj. Alpha is a non-zero scalar. Rule of replacement. Example 3.21. Use elementary row operations to transform the given matrix A into A, an upper triangular matrix, B, an identity matrix. A equals 3 12 6 1 1 1 1 2 3. Solution. Consider the given matrix A. First let us transform the matrix A into an upper triangular. This can be done as follows. A equals 3 12 6 1 1 1 1 2 3. R1 rightward arrow 1 3. R1 1 4 2 1 1 1 1 2 3. Scaling R1 R2 rightward arrow R2 plus 1 R1 R3 rightward arrow R3 plus 1 R1 1 4 2 0 3 3 0 2 1. Replacing R2 and R3. R2 rightward arrow 1 3 R2 1 4 2 0 1 1 0 2 1. Scaling R2 R3 rightward arrow R3 plus 2 R2 1 4 2 0 1 1 0 0 3. Replacing R3 120. Hence, the matrix 1 4 2 0 1 1 0 0 3 is an upper triangular, which is obtained from A by elementary row operations. B. To transform the matrix A into a diagonal matrix, we simply change all the entries above the main diagonal into zeros and the entries in the main diagonal into 1. Let us denote the above upper triangular matrix by B. Then we have B equals 1 4 2 0 1 1 0 0 3. R3 rightward arrow 1 3 R3 1 4 2 0 1 1 0 0 1. Scaling R3 R2 rightward arrow R2 plus 1 R3 R1 rightward arrow R1 plus 2 R3 1 4 0 0 1 0 0 0 1. Replacing R1 and R2. R1 rightward arrow R1 plus 4 R2 1 0 0 0 1 0 0 0 1. Replacing R1. Thus, I3 equals 1 0 0 0 1 0 0 0 1 is the identity matrix obtained from A. Definition 3.17. Two matrices are said to be raw equivalent if one can be obtained from the other by a sequence of elementary row operations. Example 3.22. Let A, B, I3 be the matrices in example 3.21. Then, A is row equivalent to both B and the identity matrix I3. Also the matrix B is row equivalent to the identity matrix I3. Exercise 3.4. 1. Given the matrix A equals 4 3 2 1. Use elementary row operations to find the lower triangular matrix which are row equivalent to A. 2. Given the matrix B equals 0 1 1 1 0 1 1 1 0. Use elementary row operations to find an identity matrix which is row equivalent to B. 3.5 Row echelon form and reduced row echelon form of a matrix. In order to find the rank, or to compute the inverse of a matrix, or to solve a linear system, we usually write the matrix either in its row echelon form or reduced row echelon form. 121. Definition 3.18. An M times N matrix is said to be in echelon form, or row echelon form, if the following conditions are satisfied. 1. All non-zero rows are above any rows of all zeros. 2. Each leading entry of a row is in a column to the right of the leading entry of the row above it. A leading entry refers to the leftmost non-zero entry in a non-zero row. 3. All entries in a column below a leading entry are zeros. If a matrix in row echelon form satisfies the following additional conditions, then it is in reduced echelon form, or reduced row echelon form. 4. The leading entry in each non-zero row is 1. 5. Each leading one is the only non-zero entry in its column. A matrix in row echelon form is said to be in reduced row echelon when every column that has a leading one has zeros in every position above and below the leading entry. Example 3.23. The given matrices A, B, C, D are in row echelon form. A equals 1100500001. B equals 40000000. C equals 10520013. D equals 12005100. And the following are in reduced row echelon form. P equals 1000100001. Q equals 1000140000. R equals 10020012. S equals 11001000. Theorem 3.6. Uniqueness of the reduced echelon form. Each matrix is row equivalent to one and only one reduced echelon matrix. Definition 3.19. A pivot position in a matrix A is a location in A that corresponds to a leading one in the reduced row echelon form of A. A pivot column is a column of A that contains a pivot position. A pivot element is a non-zero number in a pivot position that is used as needed to create zeros via row operations. 122. To write a matrix in reduced echelon form. 1. Begin with the leftmost non-zero column. This is a pivot column. The pivot position is at the top. 2. Select a non-zero entry in the pivot column as a pivot. If necessary, interchange rows to move this entry into the pivot position. 3. Use row replacement operations to create zeros in all positions below the pivot. 4. Cover, or ignore, the row containing the pivot position and cover all rows, if any, above it. Apply steps 1 to 3 to the submatrix that remains. Repeat the process until there are no more non-zero rows to modify. 5. Beginning with the rightmost pivot column and working upward and to the left, create zeros above each pivot. If a pivot is not 1, make it 1 by a scaling operation. Example 3.24. Find the reduced row echelon form of the matrix A. A equals 002302010115. Solution. Step 1. Here, the leftmost non-zero column is the second column. Step 2. By row interchanging rule, we can obtain the pivot position as follows. 002302010115 R1 left right arrow R3 011502010023 Step 3. Now, the leading entry is 1, and to create zeros in all positions below the pivot, we use the replacement rule. R2 rightward arrow R2 plus 2 R1 011500290023 Step 4. Now we proceed to the second row. Here, the leading entry is 2. Using a scaling rule we obtain a leading 1. R2 rightward arrow, 1 2, R2. 01150019200023 123 and applying row replacement rule. R3 rightward arrow R3 plus 2 R2 01150019200006 and scaling R3. R3 left right arrow 1 6 R3 01150019200001 Step 5. Beginning with the rightmost pivot column, we create zeros above each pivot element. That is, we start from the fourth column. R1 rightward arrow R1 plus 5, R3, R2 rightward arrow R2 plus 9 2, R3. 011000100001 and using row replacement to create zeros above the pivot element in the third column. R1 rightward arrow R1 plus 1 R2 010000100001 Thus, the required matrix in reduced row echelon form is given by A equals 010000100001. Exercise 3.5. 1. Determine which matrices are in reduced row echelon form. A equals 120017, B equals 100000120000. C equals 11000500012040000013. To give the row echelon form and also the reduced row echelon form of the following matrices. A equals 1 2 3 2 1 2 3 0 0 3 2 1. B equals 1 2 1 3 3 2 1 0 3